Greetings and welcome back to our next online lecture for CHE 2300. In this lecture we are going to be looking in more detail at convective heat transfer. So to start off, we're going to imagine the following scenario. We have a solid wall that has a thickness of x sub w. And on both sides of that wall we have a fluid flowing. On the left hand side we have a hot fluid, T sub H, and we have a cold fluid, T sub C. If I want to describe the general or overall heat transfer process that's going to occur from the hot fluid to the cold fluid, what I'm going to see is that I will have convection to the surface of that solid wall. I will then have conduction through that solid wall, and then on the on the right hand side I will have convection from that wall to the cold fluid on the right hand side. As we've seen previously, we can define the heat flow as the temperature difference between the hot and cold side divided by the sum of the thermal resistances. In our case, we have three resistances: one for the convection to the wall, two conduction through, and three convection from the wall. So we can write that as 1 over our convective heat transfer coefficient on the hot side multiplied by the area plus the thickness of our wall, the thickness of our wall divided by the thermal conductivity of the wall multiplied by the area plus 1 over the convective heat transfer coefficient on the cold side multiplied by the area. And then we have our delta T in the numerator. So one thing I do want to make sure I point out, different from last lecture when we were talking about heat flow through a pipe, where the pipe radius changes as we move radially out, therefore changing the area through which heat flow occurs. Here we're talking about a planar wall, so the cross-sectional area or area through which heat transfer occurs remains constant, and we can simply define an A, or area, for this problem. We know that the overall heat transfer coefficient can be defined as U is equal to 1 over the area times the sum of those thermal resistances. So we have 1 over the convective heat transfer coefficient on the hot side plus the thickness of our wall divided by the thermal conductivity of our wall plus 1 over the convective heat transfer coefficient on the cold side of our wall. And this arrow is supposed to come all the way up here because I want to make a note or highlight that oftentimes the wall resistance is typically small compared to that of the fluid resistance, or conduction in our system is typically not what governs heat transfer. Right? It's typically governed by these convective heat transfer coefficients. And so we can ask ourselves fundamentally, what are these heat transfer coefficients? We can define the heat transfer coefficient on the hot side as the flux at the wall on the hot side divided by that temperature difference between the hot fluid and the wall on the hot side of the fluid. Then we have our convective heat transfer coefficient on the cold side. This is equal to the flux at the wall on the cold side, and that is divided by the temperature of the wall on the cold side minus the temperature of the cold fluid. The heat flux at the boundary is equal to the heat flow through the solid by conduction. Mathematically, what I'm saying here, so local heat flux at wall. Mathematically, what I'm saying is that the heat flux is equal to the negative of the thermal conductivity multiplied by the temperature gradient at the wall. Right, so this conductive term here is again from Fourier's law of heat conduction, which tells me that the flux is equal to the negative of the thermal conductivity multiplied by the temperature gradient. Here we're just defining those terms specifically at the wall of this solid slab. Therefore, H, and I'm just going to pick an H, we'll say HH, becomes negative of my thermal conductivity multiplied by the temperature gradient at the wall on the hot side divided by the temperature of the hot fluid minus the temperature of the wall on the hot side. If I take that equation and I multiply both sides by a characteristic length, L sub S, and do a bit of rearranging, I obtain the following equation. Right, and this equation tells me that the convective heat transfer coefficient multiplied by this characteristic length scale and divided by the thermal conductivity is equal to the negative of this characteristic length scale multiplied by my temperature gradient divided by my temperature difference between the hot fluid and the wall next to the hot fluid. This ratio here of my convective heat transfer coefficient and my thermal conductivity is what is known as the Nusselt number. Again, we are chemical engineers, so you need to embrace the idea of dimensionless numbers. These are going to pop up much more frequently during heat transfer than they did during fluid flow. Right, up to this point, the Reynolds number is really the only dimensionless number that you've had to concern yourself with. Now I'm introducing a new number, and this new number again is called the Nusselt number. In a more general form, the Nusselt number is equal to the convective heat transfer coefficient multiplied by that characteristic length scale and divided by my thermal conductivity. I've mentioned this before, but these dimensionless numbers in chemical engineering, they represent a ratio of two competing physical phenomena that are occurring in our system. This Nusselt number represents the ratio of convective heat transfer to conductive heat transfer. Right? Again, this is our thermal conductivity, and this is our convective heat transfer coefficient. So the Nusselt number is the ratio of convective and conductive heat transfer. The characteristic length is governed by the geometry of the scenario. So for example, in pipe flow, where we have cylindrical coordinates, that characteristic length scale is the diameter of the pipe. In my equation, my Nusselt number equation becomes the convective heat transfer coefficient multiplied by the diameter of the pipe divided by the thermal conductivity. And this would all be equal to, in terms of the temperature gradient or driving forces, we have the temperature gradient at the wall divided by this average temperature gradient across the entire wall. So in reality, right, you can also think about the Nusselt number looking like this. Where again, we have our convective heat transfer in the numerator and our conductive heat transfer in the denominator. However, in the real world, it is not easy to evaluate that temperature gradient on the right-hand side of the equation. So oftentimes what you're going to find is that you will have to use empirical correlations that will allow you to calculate this Nusselt number, or either based on the Nusselt number be able to calculate this convective heat transfer coefficient. Again, the lecture today is focusing on these convective heat transfer coefficients and how that relates to our new dimensionless Nusselt number. I've included a table here of typical H values just to give you an idea of the range of magnitudes that these convective heat transfer coefficients can have, right, ranging anywhere from around 0.1, 0.2 all the way up to around 20,000, 10,000 if we're talking about BTUs per foot squared hour degrees Fahrenheit. Right? These two things are pretty interesting. Right? You'll learn or experience these a bit more when you get into the heat transfer lab, 307. But here you see this significant increase in terms of heat transfer as I go from film-type condensation to drop-wise condensation. In order to achieve drop-wise condensation, my pipes or my surface need to be coated with some type of material that doesn't allow my film to actually, doesn't allow my condensing liquid or liquid to form a film on the pipe as it condenses. We won't get into that too much in this course. We will talk a bit about heat transfer via condensation, but I did just want to put this table in there to highlight the large range or magnitudes that these convective heat transfer coefficients can have. Okay, as mentioned above, with the difficulty in measuring the temperature gradient at the wall, the convective heat transfer coefficients must be calculated from empirical correlations. Only for a few simplified cases can the correlation be derived analytically. So let's look at one of those simplified cases. In the following scenario, we have a fluid with a uniform temperature T infinity, and it is moving at a uniform velocity u sub naught, and it flows past a horizontal plate as shown in the figures below. So we are going to at first concentrate on the following figure, where for some distance x sub naught, the temperature of the wall is being held at T infinity. Then after x sub naught, the temperature of the wall changes, and it changes to this value of T sub W. And what you see here in the picture is a schematic representation or illustrative representation of the hydrodynamic boundary layer and the thermal boundary layer. And so I'm not going to say too much about this at this second, but we will circle back to this in a couple minutes. Note, the thermal boundary layer is not necessarily the same thickness as the hydrodynamic boundary layer. And we will see shortly how we can characterize the difference in thickness of those two boundary layers. So based on part B in our figure, we have the temperature equal to T infinity from 0 to some position x naught, and then after that, for all x's, the temperature of the wall is equal to T sub W. If we assume that the following parameters are temperature independent, density, conductivity, specific heat, and viscosity, a detailed analysis of the situation yields the following equation. The temperature gradient at the wall is equal to .332 multiplied by the temperature of the wall minus T infinity divided by 1 minus the ratio of x naught to x, which is our position variable, raised to the 0.75, all of that raised to the 1/3, and then those multiplied by Cp, our viscosity, our thermal conductivity, that is raised to the 1/3, and that is multiplied by the velocity, u sub naught, the density, the viscosity, and again our position x along the plate. If we recall the definition of H from the previous page in our lecture notes, we saw that H equals the negative of the thermal conductivity multiplied by that temperature gradient at the wall divided by T minus TW. Okay, letting H be the local heat transfer coefficient H sub x and T equal to T infinity, right, we get H sub x is equal to K times dt dy at the wall, so our temperature gradient at the wall divided by the temperature of the wall minus T infinity. If we substitute equation 1 into equation 3, we get the following equation for our local heat transfer coefficient H sub x. So equal to 0.332 multiplied by the thermal conductivity. That is divided by that same ratio of 1 minus x naught divided by x raised to the 0.75. All of that raised to the 1/3. And then we multiply that by C sub P mu divided by K to the 1/3 and multiplied by our velocity, density, viscosity, and position, now to the 1/2 power. Excuse me, this Yes, this should already be to the 1/2 power. My apologies for that. Yep, because all I've done is divide that over, plug that in. Okay. So there we have our equation for the local heat transfer coefficient. I can now take that equation and multiply through by the ratio of x divided by k. And when I do that, I get the following equation that you see written in your notes. I'm going to rewrite this equation in terms of dimensionless numbers. So the Nusselt number, or the local Nusselt number, again, this is a function of x, is equal to our local convective heat transfer coefficient multiplied by our position divided by the thermal conductivity. Again, that is our general form for the Nusselt number. It is a ratio of convective and conductive heat transfer. That is equal to 0.332 divided by 1 minus x naught divided by x raised to the 0.75. That entire thing raised to the 1/3 power. And now what I'm going to do is define a new dimensionless number, and hopefully you recognize, let me circle it in a different color. Hopefully you recognize that the number that the variables that I have circled in green are analogous to the Reynolds number. So the new dimensionless number that we will introduce here is the Prandtl number. And then we have our Reynolds number in green. So our Prandtl number, as you can see from the circled variables in blue, is a ratio of Cp mu divided by K. Our local Reynolds number, I'll rewrite it, even though we should all know what the Reynolds number looks like. That's our local Reynolds number. Again, it's local because it's a function of how far along the wall we are. Okay, we've seen the Nusselt number, which is a ratio of convective and conductive heat transfer. And now you are seeing a new dimensionless number, which is the Prandtl number, which is a ratio of the momentum diffusivity to the thermal diffusivity. This is our momentum diffusivity. This term is our thermal diffusivity. Right, so they are equal to what you see in the numerator and denominator on the right-hand side of that equal sign. If we do a bit of simplification, we end up with the ratio that you see in the equation above. So again, let me say this. The Prandtl number is a ratio of the momentum diffusivity to the thermal diffusivity. If the Prandtl number is greater than 1, which is true for most liquids, the thermal boundary layer is thinner than the hydrodynamic boundary layer. If the Prandtl number is greater than 1, the thermal boundary layer is thinner than the hydrodynamic boundary layer. So we'll go back up here. Now we'll focus our attention on the top one just to prove the point here. This scenario we are showing is for a Prandtl number greater than 1. Because again, for a Prandtl number greater than 1, the thermal boundary layer is thinner than the hydrodynamic boundary layer. If we look at that in terms of what the Prandtl number represents, we can see that Y, for most liquids, this Prandtl number is greater than 1, right, due to this viscosity. So Prandtl number greater than 1 for most liquids. Right? That physically is saying that the perturbation of the wall in terms of temperature does not propagate as far into the liquid as does the perturbation of the fluid simply flowing past that solid boundary. Right? This hydrodynamic boundary layer is the layer over which my velocity is changing based on the fact that I'm flowing past this solid surface. So for most liquids, the depth at which that perturbation goes away from the wall is thicker than the thermal perturbation that occurs if I were heating that wall. The opposite is the case for most gases, where we have Prandtl numbers less than 1. Right? This can be thought of in the same way in terms of the viscosity, because the viscosity of a vapor or a gas is much, much smaller, right, than a liquid. And so we end up in these scenarios where more often than not, when we're talking about gases, we are dealing with Prandtl numbers less than 1. So before I move away from that, I want to make sure that I say that again as clearly as possible. In this scenario where the Prandtl number is greater than 1, right, I have Cp mu K. Right. If I have this scenario that is shown here in 12a, what that means is that the perturbation due to this wall being heated, right, the delta T from the wall to that boundary layer is thinner than the delta velocity from that wall to the hydrodynamic boundary layer, meaning that that solid surface, as the fluid flows over it, has a higher impact on the velocity, meaning it changes the velocity over a further thickness away from the wall than does the temperature propagate away from the wall in terms of the thermal boundary layer. So if the Prandtl number were less than 1, and I were to draw that same scenario, right, in my case, I'm going to do thermal in red and hydrodynamic in blue, so it would look like this. Okay, hopefully that makes sense to everyone. Please let me know if it does not make sense. We're going to keep chugging along. Okay, so when the plate is heated over the entire length, meaning I am now eliminating this and I am moving towards this scenario where I'm heating over the entire length of the pipe, the wall temperature is TW starting at x equals 0. I get the following equation for the local Nusselt number. That x, that sub x on the Reynolds number, this should be a local Reynolds number, and we can call this a local Reynolds number. just to make sure we're differentiating it from the typical Reynolds number, which is not a function of position along a plate. This gives us an expression, so let's get back down here. This gives us an expression for the local value of the Nusselt number. Again, the local value, because the Reynolds number is a function of position along the length of that plate. It is more useful to obtain an expression for the average value of the Nusselt number over the entire length of the plate, x sub 1. So length of plate is equal to x sub 1. So to get an average value for my convective heat transfer coefficient, I integrate from 0 to x sub 1, the length of my pipe, using the expression for my local convective heat transfer coefficient. In doing this, it yields the following equation for the Nusselt number. It is equal to the convective heat transfer coefficient times x sub 1, which is the length of my plate, divided by the thermal conductivity. And this is equal to 0.664 times the Prandtl number to the 1/3 times the Reynolds number to the 1/2. In this case, the Reynolds number x1 to the 1/2. Where Rex is equal to our velocity, our density, the length of our plate, divided by the viscosity of our fluid. Let me see if I can write this for the 15th time correctly. Alright, that's the best I'm going to do. There are a couple of restrictions for equation 8. The first of these being that we have laminar flow, and the second of these being that our Prandtl number is greater than or equal to 1. I have this caveat here that it can be used with gases for Prandtl number greater than or equal to 0.7 with minimal error, so 5 to 10% error if we're using that with gases for Prandtl numbers that are greater or equal to 0.7. On the last page, I have given you Prandtl numbers for various fluids. As I mentioned above, most liquids have Prandtl numbers that are greater than 1, meaning that the hydrodynamic boundary layer is thicker than the thermal boundary layer. And then we have our gases here, which have Prandtl numbers less than 1. And for both air and CO2, our Prandtl numbers at room temperature are greater than or equal to 0.7. So we would be able to use the equation right here, equation 8, to calculate a convective heat transfer coefficient for flow of air over a heated plate. That would still be valid given the Prandtl number range here. So that should conclude our introductory lecture to convective heat transfer. I promise you there will be more moving forward as we start to talk about convective heat transfer coefficients for flow in pipes and not just flow over flat plates.